Hey guys, so we are starting 4.2. The title is called Complex Zeros and Fundamental Theorem of Algebra. Okay, so the first vocab is called the imaginary unit, which is denoted by I. Remember this? Okay, and I equal to the square root of -1. Or if I have I square, that should equal to a -1 without the square root symbol. Okay. So, and the reason I square equals -1 is because if I have I times I, okay, I'm going to go from I times I, that means that's I square, okay. That means if I'm squaring this left side, I should square this right side. So -1, square root of -1 square, so that means I square equals -1. That's how they came up with that. Okay. Now, complex numbers are numbers in the standard form. Ooh, there's a fly flying around. In standard form of, let me move this over, A plus BI. Okay, let's define what A is and what B is. Where A and B are real numbers. Okay. So remember, I want to put this in parentheses because it's super important. And let's do a period. Complex numbers, it includes, okay, complex numbers includes real numbers as well. Okay, so I want you to keep in mind it's not just imaginary, it also includes real numbers, okay? Now, in the case where you have only imaginary present, it's called pure imaginary. Okay, that means pure imaginary numbers are, okay, just called BI. Okay, then for example, some examples would just be 5i, okay, that's pure imaginary, or -10i. Okay, those are all pure imaginaries. Now, this form right here, okay, the complex numbers can be as follow. Complex numbers, examples are, i.e., okay, for example, I can go 8 plus 5i. Okay, because it has real number and then imaginary, so now it's called a complex. Okay, then I can also write 100. Okay, this is real number, but it's also part of my complex. Okay, and I can even do -1 minus, really, let's see, 3i. Okay, these are all examples of complex numbers. All right, so let's do or read this box, and we can, and again, remember, this is so important. Complex numbers also mean real numbers included. Okay, let's move into this box so we can read this definition. All right, a variable in the complex number system is referred to as a complex variable. Okay, a complex polynomial function f of a degree n is a function of the form. Now, this form right here is exactly the same form as any normal polynomial function. So there's no difference here. F of x equals a subscript of n times x to the power of n plus a subscript of n minus 1 times x to the power of n minus 1 plus ... plus a subscript of 1 times x plus a sub 0, where a sub n minus 1, a sub 1, a sub 0, these are all the leading coefficients, are complex numbers. That means it can be, okay, it can be real. So don't be scared of that word complex. It can be imaginary and it can be real. Where a sub n can never be 0. That means this first term right here cannot be 0, okay? N is a non-negative integer, okay? This is the same power. This is saying, hey, the power has to be positive. And that's still the same definition of a regular polynomial. and x is a complex variable. Complex variable is meaning that when I solve for x, I can have real or imaginary, okay? As before, a sub n is called leading coefficient of f, okay? I mean, my first one. A complex number r is called a complex zero, okay? So that means the only difference now, we're replacing the word real zero with complex, but no other are changed. Like, for example, the method of solving it is still the same, okay? But now when you're solving for complex zeros, we have to find all solutions. That's all it means. All right, guys? Moving on to our next definition. All right. Next definition. Every complex polynomial function f of x of degree, when it's greater than or equal to 1, has at least one complex zero. Okay. This is very different from real zeros. In the real zero world, real zeros, we say that it has at most, it had at most n zeros. We say at most n zeros, okay? Which is different. This one says at least. Okay, so see how the two are different from each other. Every complex polynomial function f of x of degree n, when it's greater than or equal to 1, can be factored into n linear factors, not necessarily distinct. I mean, they don't have to be different, of the form. Factor out your leading coefficients. So now you have the quantity of x minus my first 0 times the quantity of my next 0, dot, 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 and times the quantity of my last 0. Where a sub n, first r, second r, and as many r's you have, are complex numbers. That is, every complex polynomial function of degree n, when it's greater than or equal to 1, has exactly n complex 0. This is so important, okay? Some of which may repeat. So what does that mean? Okay, so this means, let's give you a polynomial function. F of x equals 4x to the 5th plus 12x to the 4th minus x minus 3. Okay. In the real world, okay, this is example 3b, and we did this in class. In example 3b, we said, hey, this have at most 5 real solutions, okay, in the real world. Now, in the complex zero, we're going to say that this has exactly 5 complex solutions. Okay. The reason is, if it's not real, then it's going to be imaginary, and both are included under complex. Okay. Versus over here, if it's not real, then it's imaginary, and I can't include it when it's said real. See the difference between the two? All right, let me zoom out a little bit. Conjugate pairs theorem. Oh, this is so important, okay? Conjugate's pair theorem says, let f of x be a polynomial whose coefficients are real numbers. If r, which is usually denoted as one of my zeros, equal to a plus bi, okay? So if r equals a plus bi is a zero of f. In this case, it's a complex zero of f. Then the complex conjugate, this is denoted as a conjugate, a minus bi, is also a zero of f. Okay, what does that mean? So let's say that I gave you, we're solving for x. Okay, I'm giving you some random f of x, and I said, hey, zeros are, let's give you, let's see, 6, -1, -5 plus 4i. Okay, so these are my zeros. Well, right away, I know, because this is, it has an imaginary number in it, okay? An additional complex zero has to be, the conjugate, which is, we're going to keep the first two numbers exactly the same. Conjugates mean we're changing this middle sign, so minus 4i. Okay. Now this theorem is not true for real zeros, but when it comes to complex zeros, it has to be true. If there's a complex zero, then we know the conjugate's got to be there. Okay. So with that last theorem, we're gonna do example 1, and this will conclude our notes. Okay. Find the remaining zeros of f. They gave you a degree of 6. The first zero they gave you is I. The next one is 3 minus I, and negative 2 plus. You know what? Can you do this for me? Can you do, that's an I. When I type, the small letter I the computer tends to change it to capital I because it's talking about me. And sometimes I just forget or didn't catch it. Okay. So it says find the remaining zero. So remaining zeros are, right, according to our conjugate pairs theorem. It's super important that you understand this. If this is an I, that means it's a conjugate. It's going to be a negative I. Okay? An I, meaning that I can write it as 0 plus I. So conjugate would be 0 minus I. But 0 minus anything it's itself, so we can just write a negative I. Then the conjugate of 3 plus 2i would be a 3. I'm sorry, I just gave you the answer, didn't I? A conjugate of 3 minus 2i would be a 3 plus 2i. Okay? And the conjugate of negative 2 plus I would be a negative 2 minus I. Keep in mind, the signs, okay, only change right in the middle, not the first, just in the middle. So you guys have to be very careful and box that up. All right. And let's count to see how many zeros we have. 1, 2, 3, 4, 5, 6. And this polynomial function, it says it has a degree of 6. Therefore, we need exactly 6 complex zeros. Okay. This one has a degree of 4. It gave us, you know what, can you fix this for me? This was supposed to be a 2 minus I, comma I, like that. Okay. All right. So it gave us 2 complex zeros. So remaining zeros are. So the complex of 2 minus, not the complex, the conjugate of 2 minus I is going to be 2 plus I. And the conjugate of a positive I is going to be a negative I. So that's all we have to do. If all they are asking you is to find the remaining zeros. And class, this is the end of our notes. Okay, we will do this in class. If you feel like you want to do this now, you can do it now, but you don't need to do it now if you don't feel like it. All right, have a great day. Go and complete your assignment. Okay, you still have some more problems to do if you didn't get a stamp in class already. Have a wonderful day.